Hi everyone. So far we have discussed about single rate systems in which single sampling rate is used. These systems that use single sampling rate from A to D converter to D to A converter are known as single rate systems. But now we are going to extend our discussion on systems where the sampling rate of the signals are unequal at various parts of the system, which means the discrete time systems that process data at more than one sampling rate are actually known as multi-rate systems. There are many cases or applications where multi-rate signal processing is required. They are in high quality data acquisition and storage systems, in audio signal processing, in video, PAL and NTSC run at different sampling rates. Therefore, to watch an American program in Europe, one needs a sampling rate converter. It is also used in speech processing to reduce the storage speeds or the transmitting rate of speech data. In transmultiplexers and narrowband filtering for fetal ECG and EEG. There are so many applications like this that there are two basic operations in multi-rate signal processing. They are decimation and interpolation. So decimation reduces the sampling rate, whereas interpolation increases the sampling rate. So today's topic is decimation by a factor D. What is this decimation by a factor D? As told already, the sampling rate of a discrete time signal x of n can be reduced by a factor D by taking every dth value of the signal. That is, this is actually the block diagram representation of the downsampler. So this is the symbol for downsampling, which is pointing downwards. The output signal y of m is a downsampled signal of the input signal x of n, and we are representing it like this. So what are the sampling frequencies at the input? Sampling frequencies at the input is fx is equal to 1 by tx. When it passes through the impulse response h of n, we are getting v of n. And this v of n is downsampled by a factor d in order to get y of m. There the sampling rate or the sampling frequency fy is equal to fx divided by d. Right. So let us assume the signal x of n as shown in the figure. Downsampled x of n can be obtained by simply keeping every dth sample and removing d minus 1 in between the samples. So this process is equal to reducing the sampling rate by a factor d. Right. So the signal x of n is downsampled to get the output. Right. So here the magnitude function hd of omega can be written as it is equal to 1 for the limits omega takes the value lesser than or equal to, instead of pi we have pi divided by d. So 0 otherwise. Now we are considering the output of the system, that is v of n. V of n is equal to the convolution of impulse response and the input of the system. So what is y of m then? The same thing, v of n convoluted with the h of n, but with the downsampling value or factor d. Right. So is the decimation an LTR operation? Yes. So this is a graph which will explain us in detail what is happening in decimation. Right. So let us consider the signal x of n, and the z transform of the signal we know is x of n is given by x of z is equal to summation of n equal to minus infinity to infinity x of n into z to the power of minus n. Let's say that is our input signal. So the downsampled sequence is actually y of n. The expected one is y of m. Right. So this is obtained by multiplying the sequence v of n. So v of n is the sequence which is given here, is obtained by multiplying v of n and a periodic train of impulses p of n with the period d, and then leaving out d minus 1 zeros between each sample. So as shown in the figure. So the periodic train of pulses p of n is given by P of n is equal to this equation 1 divided by d into the summation of k equal to 0 to d minus 1 and e to the power of j 2 pi k n divided by d. This is actually the discrete Fourier series representation of the periodic train of pulses, right? So while multiplying the two signals, that is v of n and p of n, we will get v tilde of n, right? So if we leave d minus 1 zeros between each sample, we will get the value of y of n. So y of n is equal to v tilde of nd, that is leaving d minus 1 zeros between each sample, we will get the value of v of nd, right? So y of n can be obtained by using v bar of md, which is nothing but v bar of md, v of md into p of md, which is equal to v of m into d, because p of m into d is a periodic sequence, right? So the z transform of the output sequence is actually given by y of z is equal to the summation of m equal to minus infinity to infinity y of m into z to the power of minus m. We know what is y of n from the previous expression, so they substitute that here. Y of z can be written as, since this is actually decimations, we are simply raising it to the power, so z to the power of minus m divided by d. V bar of n is equal to v of n into p of n, where p of n we have already discussed. This is the discrete Fourier series representation. Now substitute this here and multiply it, we will get this expression. So 1 divided by d into the summation of k equal to 0 to d minus 1 hd of e to the power of this one and x of this one, right? So v of n is actually the convolution of input signal x of n and h of n, where hd of omega we already know, we have discussed this, right? So from this above relationship, we can find that if the Fourier transform of the input signal of a downsampler is x of e to the power of minus j omega, then the Fourier transform of y of e power j omega of the output signal y of n is a sum of d uniformly shifted and stretched versions of x of e to the power of j omega scaled by a factor of 1 by d. So if we are considering an example, evaluate the Z transform on unit circle with frequency variable y of omega, that is angular frequency, is equal to 2 pi f divided by fy, which can be written as 2 pi f into ty, because fy is equal to 1 divided by ty, right? So fy can also be written as fx divided by d, because the input sampling frequency is fx. So omega x is equal to 2 pi f divided by fx, which can be rewritten like this. So from these two expressions we can rewrite omega y is equal to d into omega x. So the at the input, the sampling frequency or the angular frequency of the signal is varying from 0 to pi divided by d. It is now getting stretched to 0 less than or equal to omega y less than or equal to pi by downsampling, right? So once again rewrite the expression. This is what I told you. So if the spectrum of the original signal x of e power j omega is band limited to omega is equal to pi divided by d, the spectrum is being periodic with the period 2 pi. That is what is the understanding. The spectrum of the downsampled signal y of e power j omega is the sum of all uniformly shifted and stretched versions of x of e power j omega scaled by a factor of 1 divided by d, right? So this is what is the understanding. Y of omega y is equal to divide 1 by d into hd of this one, or it can be written as 1 divided by d into x of omega y divided by d. So it can be represented graphically like this. So the input signal x of omega x and v of omega x, he of omega x and y of omega y. So this is how the signal is getting transformed when we are introducing a factor of d decimation. Thank you.